Now, the Rayleigh distribution is a bit more obscure, but still occurs in some very crucial scenarios. Let's say, for instance, that you're investigating a random variable that is itself made up of the sum of other random variables. Now, during these investigations, at some point, you want to look at the variance of the distribution of your random variable. Now, because your random variable is the sum of other random variables, and each of these distributions of these random variables have their own variance, what you might want to do is to add up all of these variances. In this way, you're adding up squared numbers, because the variance is the square number of the standard deviation. In this example, where you have the sum of squared numbers, for which these numbers are random variables, is described by the Rayleigh distribution. Another example are wind speeds, because wind speeds are also a random variable that is made up of the sum of the square of two other random variables, if you're working in 2 dimensions. The Rayleigh distribution also occurs a lot in physics. Now, if you look at the visualizations here, then we can learn a few things. First of all, the distribution function seems to be a skewed normal distribution, but it definitely is not that. And if we again want to verify our heuristic, namely that the slope of the cumulative distribution function indicates where most of the data lies, then we indeed see that the slope is much larger at the start and then tapers off nearing the end. And that's exactly what we see here, because most of the data is on the left-hand side. And then again, we will go to the code one last time to see how we can generate population samples that are distributed according to the Rayleigh distribution. Again, we only have one parameter, the Rayleigh scale, and the Rayleigh distribution is then simply numpy.random.Rayleigh, our scale, and the size. And this brings us to the end of this lesson, and in fact to the end of chapter 5, where we delve deeper into the world of distributions. Now, to be sure, you don't have to learn all of these distributions by heart and what parameters that they need. It's just important that you realize that there are various different distributions, but nonetheless that one distribution can have a lot of distinct real-life data sets that are approximated by it. In the next chapter, we will finally cover the ultimate tool in statistics, namely the p-value. Because at this point, we have enough knowledge and insights, and we are familiar enough with the tool of simulation that we can get an intuitive grasp on this abstract concept in physics. So I will see you in the next chapter.